back over and move the black over. So we can keep doing that until we've exhausted all the possible single ones, right? How many arrangements? 4. 4 possible microstates within that one. I am going somewhere with this. So yeah, in the case where we have 3 on the left and 1 on the right, there are 4 possible. There's more of a probability that we could have 3 on one side and 1 on the other than having 4 on one side and 0 on the other. Okay, now changing this again to where I have 2 and 2. 2 particles on the left and 2 particles on the right. If I had maybe a black and a red on the left, and a green and a blue on the right, the macro state would be 2 on the left and 2 on the right. How many microstates are there? How many? 6. Anybody agree with that?
Sure.
Yes, I agree because it's Danny.
That's the only thing I know.
Okay, we could have on the left black and red, that's 1. Black and blue, that's 2. On the left black and green, that's 3. On the left red and blue, that's 4. On the left red and green, that's 5. And on the left blue and green, that's 6. I think we've hit them all. So 6 possible microstates or configurations. So when we have 2 and 2, there are 6 possible arrangements. Now, I think it would be easy to tell that if we went to the macro state, 1 on the left and 3 on the right, how many microstates are there? There's 4 again, where we would have 1 in each of the color, taking that space on the left, each taking its turn. And then the macro state 0 and 4, we would go back to 1 microstate. So my question down here is, which is the most likely? If we're looking at this in terms of probability, the arrangement that has the most positional probability, the most possible arrangements, would be macro state number 3, where we have 6 possible arrangements. We would consider this arrangement to be the most entropy then, because it's got the most possible positions, the most possible arrangements. Now, there was a guy, a physicist, Ludwig Boltzmann, German guy.
Why are they all German?
A lot of them were. Yeah, back in the late 1800s, early 1900s, a lot was happening there in Germany, and they were really training up some great chemists and physicists. So now, please don't write this down and see you grabbing your pencil. You do not need to do any calculation at all with this. In physics, you might. Anybody in here had AP Physics? You're taking right now. Johnny did. I didn't ask Johnny if he ever used this one. But yeah, S is the symbol for entropy, remember. We don't have to have a delta in front of the S either. We can just have a straight up S equals Boltzmann's constant times, this is the ln, the natural log, of W, which represents the number of possible microstates. Yes?
Do we need to know positional entropy? Is that just like a concept?
Conceptually, I want you to know, and I'll be using that term a lot. I don't think you'll have any questions about it, but it helps us to understand what entropy is. Yeah, I'll use it to help introduce things with it. You'll see, but there won't be anything. You don't have to give a clean definition of it. Yes. Is what on the test? This.
Positional entropy.
No, the concept of entropy is, but specifically about positional, no.
Wait, is anything we're learning today on the test? Seems like I'm really lost with that huge
No, you'll be found in a few minutes. Just hang out. So if you take a look at this, the more possible microstates a system has, the higher the entropy. This is another way of thinking about what entropy is. Like I said, it's kind of cheap to say that entropy is just disorder. I mean, it works. Our brain can grab that. Yeah, I know what disorder is. But it's in a pure sense, it's about how many possible arrangements there are. I want you to check out this. Nothing to write down here. Just look at it. In the context of, this is a dorm room or a bedroom, not sure which, probably a dorm room. If this dorm room is real neat and tidy, that means that every single thing in the room has a place. There's a place designated for every single thing in the room. That would make it very neat and tidy. If it's messy, there's a whole bunch of different arrangements that the room can have to be messy. So, in terms of entropy, this is what Boltzmann really was saying in a conceptual sense. the more possible arrangements something has, the more entropy that it has. So if a bedroom is nice and clean and tidy, it's got one specific arrangement, and that's where everything is in its place, its designated place. But if it's a messy bedroom, there can be a lot of different arrangements of a messy bedroom. That makes the messy bedroom higher entropy. Another example of this is if I take a deck of 52 cards, throw the jokers in there too, there's 54 cards, and I throw it up in the air. You know how the deck of cards are going to go. Some of them are going to be spinning away, some of them be kind of fluttering down to the ground, they'd make a big mess on the floor. There are a lot of different arrangements for the deck of cards to fall into. Is it possible that all 54 cards would fall into a nice, neat pile on the floor? I suppose it's possible. We know it's not going to happen, though. Because it's so much more probable that it'll arrange itself, the deck will arrange itself in a very crazy pattern all over the place. Because the higher the entropy means the more different arrangements that the cards can make. So that's more likely what it's going to do. Nature has a tendency to change itself into a higher entropy state. Nature has a tendency to make itself more messy. I just have 2 slides left to do in 5 minutes. This is very quick. Be aware that when you heat something up, this is going to show us the interrelationship between enthalpy and entropy. If something absorbs heat, it's going to cause its particles to move faster. That's going to increase entropy in it. So increased molecular motion means increased entropy. And if the system can release enthalpy, can release heat to its surroundings, that means that you're changing the molecular motion of the surroundings. And so we're going to care about the delta S of the surroundings too. Now last chapter when we did thermochemistry, we talked about the surroundings a little bit, but we never really calculated anything in the surroundings. We will with entropy. The change in entropy of the surroundings is going to matter, as well as the change of entropy in the system.
What about the universe?
Okay, now what we learned about last chapter is the system plus the surroundings makes up the whole universe. Because the system is the change that we're studying, the surroundings are everything else in the world, and therefore the delta S of the universe is going to be the delta S of the system plus the delta S of the surroundings.
Do we need to calculate that?
Sometimes, yes. But it's not going to be terrible. Calculating delta S is never bad. It's just not difficult. This is the last slide that I'm going to leave you with today. This is the 3rd law of thermodynamics that we will have learned. But it's called the 2nd law of thermodynamics. Physicists. Anyway, this is a biggie. This is the most powerful to me of all the laws of thermodynamics. In order for a system to be spontaneous, for a process to be spontaneous, there must be an increase in the entropy of the universe. Nature tends to become more messy. All spontaneous processes are going to have an increase in entropy of the universe. Sometimes that will mean a system will go down in entropy, which is not favorable because that means it's becoming more ordered. But the surroundings might go up in entropy more, and therefore there's an increase in entropy of the universe.
Everything's balanced.
Not even balanced. There's an imbalance toward a higher entropy.
So if the system's
Well, no, you're saying
entropy
it's
increases, then the universe's entropy will still increase.
Yes, usually it will.
So it's not like
Yep.
a give or take.
Right, right. Yeah. So as long as there's overall an increase in the entropy of the universe, meaning the system and or the surroundings go up in entropy, as long as that net change is positive, meaning more entropy, then that will be a spontaneous process. So as somebody last hour said, does that say something about the fate of the universe? Yes, very much it does. Very much so. The universe has a tendency to become more scattered, more disordered, more spread out.
I like those. I like that.
That's great.
So yeah, enjoy your life now because it's going to become more messy.
Did you believe the whole wall died by 2012 or whatever that thing was?
Yeah, I was scared. I stayed in bed that day.
I don't even know if I even heard of it.
In fear, I thought it was for something.
I was probably studying.